You make the big yeah, I'm like here, and Tom's like here, and you're like here. No offense to you, Tom. You're also much bigger bucks than I. You make the data minus bucks. Tom makes the media minus bucks, and I make the data minus bucks. Because data mining is the biggest keyword in the industry right now. Data mining answer.
Okay, so today we have to discuss this big scary thing. This one. Slate MDP is deep neural network, deep reinforcement learning, and we also have to think about attention. So while thinking about attention, we should not lose our attention. Okay. So let's start, but before starting, so we will have your assignment 2 graded by the end of this week and assignment 3 graded by middle of next week. And we will assign you assignment 4, which is pretty simple. Whatever you did, just do it in a user independent way. So that means initially you took 80% from every user and tested on 20%. Now take 80% of the users. Take all the data of the 80% of the users, use it for training, and then don't take any data from 20% users, but use them for testing. Just that is the simple change. I'll upload the assignment document. It will be due in 2 weeks, so that means 30th April. And that will be the last assignment. We won't have any 5th assignment. So this one we will try to finish off. So this one will take a little bit of time to finish because we will have to learn a lot of things. So we will have to talk about reinforcement learning. We have already talked about, right? We know this term. We kind of know this term because we have talked about this in the last class. We know MDP very well, right? We have discussed that a lot. But we were thinking about this term, slate. So we did some thinking last time, and we will do some more thinking this time. Then we have to talk about attention. Attention will take a lot of time, right? Why will it take a lot of time? Because we will have to talk about recurrent neural networks, we will have to talk about LSTMs, and then only we can begin to think about attention, right? So there is some background work we need to do. We have talked to, did we talk about recurrent neural network a little bit? Did we talk about? Did we mention?
Yes.
We did, right? We said very small. But we will talk about the core idea or why recurrent neural network is good. We will talk about that, and we will talk about LSTMs in more detail. So that will take maybe another 2 classes. Right? So then we will be done with data mining. But then some students asked that we should cover TensorFlow. So we'll cover TensorFlow. And also somebody asked that we need to cover generative models like GANs, adversarial networks, those things. So we'll try to cover GANs. That will be later. maybe the last week or the second last week and so on. So we'll cover those. And if you have any ideas of any topics that we can cover, you can suggest me. Depending upon time, I will try to cover. Right? So remember, all these topics are new. So they are new to me also. So I don't know everything. I'll try to dig out papers and presentations that are available online, and we'll try to discuss however much I can with respect to my own research experience. We'll try to discuss. But those might not be the right things. So if you think that something I have said is wrong, tell me, then I will correct. Right? I will correct those. So I may be wrong. So let's start our discussion on deep reinforcement learning with attention for slate Markov decision processes with high dimensional states and actions. Done. So we know what is slate Markov decision process. Right? We some little bit of idea we have. So we know what is Markov decision process, and we know what is a policy in Markov decision process. Right? So we know that transitions are basically a mapping between states and actions. So in each state, what action you can take, these are the options of transition. And when we consider policy, policy is basically a one-to-one mapping. So given a state, what action you take, that is policy. And we also know the distinction between policy and execution of a policy. Policy does not limit you to time. Execution does. And execution says that, okay, it gives you a start state, which state to start from, and it also tells you how long should you execute this policy. Right? So policy is basically just a mapping between states and actions, and using that mapping, you can start from a particular state and you can use that mapping for a particular amount of time, you get a policy execution. Now slate MDPs are a bit different. In slate MDPs, policy is not just a mapping between state and action. It is a mapping between a state and a set of actions. So basically a S cross power set of actions. Typically the mapping, typically a policy means S cross A, right? Where S is the set of states and A is the set of actions. But in slate MDPs, it is S cross power set of A, so which is set of subsets of all A's, right? That is slate MDP. So just this change. Now why this change? This change is directly reflected in one particular application that we are interested in. Right? We are interested in the recommendation system, and we could draw parallels to the recommendation system. For example, if you log in at the front screen, there is a lot of options that you can take. So that is some policy. Somebody had decided to put all those tiles in the first page in Netflix, right? So it is a policy. So that means that policy gives you a set of actions that you can do. So that's why slate MDPs are very related to recommendation systems, right? And that is what Google's DeepMind uses also. So let's take a mathematical definition of slate MDPs. Why do we need to do mathematics? Because we don't like mathematics. Why do we talk about mathematics? Why? Because there is a nice property that can guide you to recommendation systems after this. So I promise you, we'll look at the nitty-gritty details, some sets and some operations on sets, but I promise you at the end you'll get something fruitful. Typically when you do research in mathematics, you don't get anything fruitful after the end. But this you'll get something fruitful. Right? So let's talk about slate MDPs. Let's go over the notations again. So we know that MDP is SATR, that we know. And what is S? S is the set of states, A is the set of actions, T is the transition, so which means so it's a mapping from states cross actions to states, which means you take a state, you take an action, and you go to a state. Right? And that is deterministic, but you can also have probabilistic, which means you take a state, you take an action, and with some probability distribution, either you go to S1 or to S2 or to S3. That is stochastic. Right? But regardless, SAT and R is what? Reward. Reward means in each state you take an action, what is the reward? You can have uniform reward for all actions in all states, or you can have different rewards. It doesn't matter. So the reward is like a mapping between states, actions, and some real numbers. Right? So SATR is an MDP, but then we extend the MDP. We extend the MDP. How do we extend? We define a few functions. So first function is phi. What is this phi? Phi is a mapping between S and A to the power L to A. What is A to the power L? What is an element in A to the power L?
L actions.
L actions, yes, exactly. Yeah, L dimensions or L actions, right? I think this is not working. So what does this phi say? This phi says that, okay, you have a state and you have L actions and output is an action. So what is this phi? It's an action selector, right? Phi is an action selector. Now in a recommendation system, you don't assume that you have phi. Typically you don't have phi. You have to learn phi. Or either you have to learn phi or you have to sense phi. How do you sense phi? Just by looking at how the user is behaving. The user might click something and that gives you phi. Right? So phi is something that you get after the fact. You don't really know phi. But regardless, phi is a function that is like an action selector. And then we define a T prime. It's a different type of transition. Right? T prime. What is T prime? T prime is basically a mapping between S cross A to the power L cross S to a probability distribution. So what is it saying? It's saying that, okay, you are in a state S and you have all this set of actions, and each set of actions will get you to a certain state. Choose one. Depending on what you choose, you might end up with different states. That is what this T prime is saying. So now, if you fix, so what does this T prime S A S prime mean? So it means that, okay, what you can do is you can fix the action. You can fix the action set phi A. So if you do T prime S A S prime, that is basically if you fix the action, then it boils down to T S phi A S prime for all phi's. So basically if you fix the action, then you get definite states. If you don't fix the action, then you get a probability of states. Right? So that is what this is saying. And then you have a similar definition for reward, because each reward is based on what action you take. Right? So R prime is a probabilistic reward function, because you don't really know which action you are going to select. You don't know. But if you select the action, you get the reward. So that's why R S phi A is the action selector. So you select the action, you go to S prime, and then you get the reward for it. So that's how R prime and T prime are defined. Right. Now they go into some mathematics which is not really, no, it is kind of related. Okay, so now we assume that the previous execution's action can be derived from the state through a function chi. So what is chi? Chi is the history. Is the user history. So what is it? It is saying that, okay, chi is a mapping from S to A. It says that, okay, what actions did you take in the past when you were in a particular state S? That is chi. So chi is the history, phi is the actual choice now. Right? So phi is the choice, chi is the history. So let's remember these terms, because these terms we'll use later to define those nice properties that I said. So let's move on, and then they give all these mathematical details. You don't really need to know this. So what are they saying? Okay, how do you get the probability that you will be in a particular state S prime, and you will get a reward R prime? How do you know that? So basically S prime, R prime given the current state and the state A. How can you figure that out? Just sum over all possible actions A and weigh in the probability that you take an action A. Right? So this is nothing but the Bayes theorem. This is simple. So again, reiterating, what does it say? It says that, okay, what is the probability that you will get to a state S prime and you will get a reward R prime, given that you are in a current state S and you have this slate A. Slate A means you can choose any of those actions. So how do you figure that out? You know that you can choose any of those actions, so that is the only variable there. So what you do is you go over all possible actions, weigh them with their probability of occurrence, and just add. And that's what the Bayes' theorem says. So that's why PR S prime R prime S given S comma A. So A is a definite action; it's not a set. And then you multiply it with the probability that given this set A, capital A, bold A, you take this action, italicized A. Right? You multiply it with the probability and you get the. So why is this necessary? This is necessary to calculate the reward or the value of a policy. Is necessary to calculate the value. So using this probability, then you can get the reward, you can get the value and all that. Let's not get into this. So this is again mathematical details. It's very simple. Right? If you think about it, if you understand these rules, Bayes' theorem, it's very simple to derive R and Q. Right? So let's not go into that. It will just waste time. That's what I'm saying. Now there is another issue. So you are saying if you think of a recommendation system, you are giving some set of movies that you can watch in the initial screen, right? Is it guaranteed that you will pick one of them? Do you always pick one of them? Or do you go into the search button and type something and then pick a totally different movie than what it was displayed in the initial screen? You do that, right? So that means you deviate from policy. You do deviate from the policy. So, how do we represent that in mathematics? Deviation of policy. How do we do that? It's very easy given this setup. So this setup says that cap A bold is the slate. Slate means the set of actions that you can take. What is shy? Shy is the history, right? So shy tells me what choices you took in the past. So if you had deviated from the policy, then what will happen is that, let's say at state S and at time t, you deviated from the policy. Then how can I represent it? I can represent it as shy and give it as input st. St means the state at which you were, the state at which you were at time t. That is st. So shy st, if it belongs to the slate A, then that means you followed the policy. And if it does not belong to slate A, then that means you didn't choose what I showed you. Right? So that means you deviated from the policy. So just using shy, the notion of time and the state you are in, and the slate, we can represent whether you were in the you were following the policy, that means you were following the recommendations, or you are not following the recommendations. We can do that. So that is what this paragraph is saying. So it's saying that in the recommendation system setting, shy t plus 1 belongs to AT means a recommendation was selected by the user. Whereas shy t plus 1 not belonging to AT means a recommendation was not selected. Now note that this is t plus 1 and this is AT. It's just modeling the progression in time. So it's saying that at time t you are given AT set, and then you make the decision at t plus 1. Right? So that's why it's modeling the progression. Not important. But that is how you can say that you followed the policy. So now in recommendation setting, you say that you follow the recommendation or not. But in a general setting for slate MDPs, you call it good states and bad states. So good states means if you have selected from the slate, it's good. If you didn't select from the slate, it's bad. Okay. Now there is the notion of value order. What is value order? So remember that you calculated R and Q. Okay, by the way, I skipped one thing I didn't mention last time. When we were talking about MDPs, I didn't mention one thing which I should have mentioned. or when we were talking about reinforcement learning, I should have mentioned one thing. So that one thing is that when we are talking about reinforcement learning, we said that you need to learn the value function, right? Now we also discussed that instead of learning the value function, maybe you learn the Q function. Q was what? The reward for that immediate step, not in the future, right? So when we learn the Q function, it's called Q learning. So that is a different, so you will find papers, you will find research that do Q learning. So what is it? So Q learning is basically reinforcement learning, but you learn the Q function instead of the value function. And we saw that learning the Q function is a greedy approach, right? It's not the optimal approach, it may not be the optimal approach, but it's a greedy approach to learning the Q function. And learning the value function is what will lead you to the optimal result, but it might not be possible all the time. Okay? So all these terms, they might linger around, and they might seem that these are big terms that industry or researchers are using, but if you understand the basics of reinforcement learning and what we are discussing, it's not that big of a deal. It's a very simple idea. The idea is simple, but the only problem is it's very complex. Complex means the idea is not complex, but solving the problem is very complex. A simple idea is resulting in a problem that cannot be solved easily. That is what is the deal these days. And since you have a very big system these days where you can run algorithms very fast, you can solve these big problems, these complex issues. That's why these are coming up now. But reinforcement learning, all these were technology 40, 50 years back. People knew about this. Any form of deep learning you talk about, people knew about this. Right? But they couldn't study this because they couldn't implement this. They couldn't run this. Now we have Titan V GPUs. Right? We have GPU clusters. Very fast. So now these are creeping up. Right? So, but the basic concepts are pretty simple. It's not that difficult. Okay. So now let's look at value order. Now let's now this is another problem with this paper. That's why I think they didn't publish it in conference. They now introduce two terms, mu and v, V2 environments. They have not defined what is an environment. Has anybody read the paper? Full? Nobody read the paper. I explained it. I don't know whether they have defined environment or not. I don't think they have defined what is environment. But they use it in a mathematical term, mu and v. Anybody knows if they have defined or not?
They didn't.
They didn't, right? Yeah, they didn't define environment, but they use it in a very specific way. They give it inputs and they get outputs from mu and v. So how will I know what is mu and v? There's no way of knowing what is mu and v from just reading their paper. So that's why I think they didn't send it to a conference. It would have been rejected. So what I am thinking is that mu and v are probability distributions. So probability distributions means that, okay, given a maybe given a state, current state, and a slate, right? What is the probability that if you take, or what is the probability of you getting a reward, right? Yes, I think that is what the environment is saying. So reiterating, the environment is like a probability distribution function. And what is that probability distribution function? It says that, okay, you are given a current state and you are given a slate of actions, right? What is the probability that you go to a particular state, S prime, different state, and you get a certain reward? I think that is what they mean by V. I have no idea. Maybe that is what. So I don't know. Then there is no way to know from reading the paper. But let's go ahead. So now they are saying, okay, let mu and v be two environments with the same state space S and action space A. Right. Now, if for any pair of policies, now they consider two policies, pi and pi hat, right? Pi and pi hat. So they are saying that, okay, these two environments, mu and v. So if I see that policy pi is better than pi hat in environment mu, and if policy pi is better than pi hat in environment mu, then it implies that policy pi is also better than pi hat in environment v, and vice versa. So if policy pi is better than pi hat in environment v, then policy pi is better than pi hat in environment u, or mu, I think. It's not v, mu and mu, very difficult to distinguish. Right. So, and they say that if that property holds, then we say that mu and nu have the same value order. So now let's understand what is an environment. Environment is basically some random process is going on, right? And you are modeling that random process using some states and actions. You are in a particular state. You have a choice of actions. You take an action, you go to a state, and you get a reward. That process, that entire process, they are calling it an environment. Right? So an environment will have a specific set of states, it will have a specific set of actions, it will have a specific set of slates, it will have a specific set of rewards. Right? When you fix those, it becomes an environment. So now you can have two different two different states, two different types of states, two different types of actions, two different types of rewards. That will make two separate environments. So let's consider two separate environments, mu and nu. Right? So they might differ in the states, they might differ in the actions, they might differ in the rewards. Don't care. Let's consider mu and nu, two separate environments. Now we are saying that, okay, mu and nu will keep the value order. Now what is value order? Value applies to policies, right? So when the moment here.
So if the reward will be different than the policy execution, then how the policy execution would you said that the v mu will be greater than the.
Yeah, I'm coming to that. I'm coming to that. Just wait a little bit and then re-ask your question. Right? Let's wait a little bit. So there are two environments, mu and everything can be different. That's what I'm saying. So regardless if they are totally different environments, value order means it has to do something with the value. If it does something with the value, then that means it has to do something with the policy. So let's consider two separate policies, pi and pi prime. Let's consider those two policies in the environment mu. So when I say the environment mu, then I fix the state, I fix the action, I fix the reward, and I also fix the slate. Right? So in that environment, let's apply pi and pi prime, and let's calculate the value for pi, prime. Turns out that the value for pi is greater than the value for pi prime, so pi is better policy than pi prime in environment mu. Now let's come to nu. Let's come to the environment nu. It's totally different states, totally different actions, totally different rewards, but the same policies. Use the same policies, pi and pi prime. Okay. Typically, if you have totally different states and totally different actions, then you cannot have same policies. Typically, so you have to have same states, same actions. Then only you can define the same policies on both the environments. Right? So typically you can say that states set and action set is the same, rewards might be different, or even slates might be different. Right? So that is you can assume. But regardless, so use the pi and pi prime in nu and calculate the value of pi and value of pi prime in nu. It will so happen, if it happens that value of pi is greater than value of pi prime. So which means if pi is also greater than pi prime in the environment nu, then we say that mu and nu maintain value order. So any two policies, pi and pi prime. If pi is better than pi prime in mu, it will also be better than pi prime in nu. If that is the case, then we say that mu and nu maintain value order. These are two separate environments. They are maintaining value order. Right? Now, how can there be separate environments? We said that maybe state is different, maybe action is different. But what if states and actions are same for both the environments? What else can change?
T and R.
What?
T and R, transition and rewards.
Exactly. Transition, rewards and slate. Right? Slate can also change. So transitions can change, rewards can change, slate can change. What happens when slate changes? Not only slate, phi can change. Phi can change and so can psi. Right? So what is phi? Phi is what choice you will take next. And what is psi? What choice you have taken earlier. So all these can change. So what if my slate changes? Then that is a different recommendation system. Right? If my slate changed, then mu and nu are two different recommendation systems. What if my phi changes? What is the parallel to recommendation system? What is the practical significance of changing phi?
User change.
User change. Yeah, exactly. User changed. Right? Or not, you cannot really say user change. You can say that the user's pattern changed. Right? So one usage pattern versus other usage pattern. It might be the same user. It might be the same user taking two usage patterns. Right? So phi is user pattern. Usage pattern changed. What happened when psi changes? What is the parallel to recommendation system? Changing of psi. What? Who answered? Somebody answered. Psi is what? Psi is usage history. Right? Psi says that whether you are following my recommendations or no. So psi changing means the user profile changing. So phi changing means usage pattern changes. Maybe the user profile didn't change, but usage pattern changes. But psi changing means the total user has changed. Right? This user is following our recommendation or not following our recommendation. So that can be the differences between the two environments, mu and nu. Right? So now they are saying that okay, what is value order? Value order means these are similar users because similar policies work on them. If two environments maintain value order, then we can say that okay, this user has the similar usage pattern as this, because if I apply pi and pi prime to this user, pi is better, and if I apply pi and pi prime to another user, pi is better, still better. Right? So that means that for these two users, same policies work. Pi works for these two users. Right? So using value order, you can classify users. So that is the interesting thing. That is what we have come up to by doing all those mathematics. We didn't do a lot of mathematics, but whatever mathematics we did is helping us. So the concept of value order is telling us that whatever policy, if two environments maintain value orders, then whatever policy I take for mu, I can take it for nu also, because this is better. So that is the significance. Now then they have some other terms. Fatal failure versus execution is best. These two are related. So then they are saying that okay, let's say there is a state called S end, right? What is S end? Send says that, okay, no matter what action you take, you are given a slate, right? You have Send is a particular state that you reached, and you are given a slate of actions. You can choose any of them. No matter what you choose, your reward is 0. It's always 0. It's going to be 0 with a probability of 1, and you will remain in that state, right? No matter what you choose. So that is, suppose that there is such a state Send. Suppose that there is such a state. Okay? So Send is a state where whatever action you choose with probability 1, you will get reward 0. And you will be in that state. There's no way out. Right? So if that is the case, then it says that, okay, if fatal failure is this. So if V, S and R equals 0 given S comma is 1, whenever psi S prime is not equal to A. So which means that you took an action which was not recommended to you. You took an action and it was not recommended to you, and you ended up in Send. Right? So which means your reward is 0 and you will remain in that state. Whatever you do, your reward will always be 0. Right? If you end up in that state, then that means you did not follow my policy, no reward. That is a fatal failure. That is called fatal failure. So if you go from one state that is not Send, and you don't follow the policy, and if you go into Send as a result of not following the policy, it's called fatal failure. So what is fatal failure? What is a practical representation in recommendation systems for fatal failure?
System crash.
No. Nothing will crash. It's just a choice of the recommender, right?
Finding unidentified users that we have still haven't been able to.
Yeah. So your recommendation is crap. It didn't work at all to the user. The user selected totally a different thing. Right? You thought the user will like comedy. You gave the user horror movies. Right? So the user went to Send and it never came back. So that means it's deleted Netflix account. No, it doesn't mean deleted Netflix account. The user is just watching all movies that you never recommended. Right? And you are not even coming up with good recommendations because the user is never relying on your recommendation. So that is a fatal failure. System won't crash, and system crash is like a very strong statement, right? And you can call this system crash. Then you have EIB, right? So then before we discuss EIB, we have to say that we have to see this definition. So V S prime R prime given S comma A is mu S prime R prime given S comma A if psi S prime belongs to A. So which means if you take an action, then let's say you get the same value. So V and mu, these are two different environments. Mu means you follow my recommendation, and V means you don't follow my recommendation. Right? So if you follow my recommendation, then V and mu are the same. But if you don't follow my recommendations, then V and mu are different. Right? So that's what it's saying, that okay, suppose that V and mu are the same if you follow my recommendation. Right? That is what this statement is saying. The statement is saying that okay, let's say not V, so nu and mu are the same if you follow my recommendation. And if you don't follow my recommendation, let's say nu is a fatal failure and mu has some reward. Then we call mu as execution is best. That means if you follow my recommendation, you will get rewards. And if you don't follow my recommendation, you will get 0 rewards. Right? So then you say mu is execution is best. So then what is the practical significance in case of a recommendation system? When is execution is best? When a person selects one of the tiles on the first page that you show it. So that means you will give a recommendation, it perfectly matched the user selected that one and gave it 5-star rating, highest reward. So that is execution is best. Right? So we won't bore you with any more mathematics here. So we'll stop here. With this paper, we'll stop here. Now, this paper has a lot of other things. Now, what are those other things? Those other things are basically how do you learn the slate, how do you learn the policy, how do you learn T prime, how do you learn T, you use reinforcement learning, you use deep reinforcement learning and learn them. And that is what the rest of the paper is. Now, you know how reinforcement learning works with MDPs. We didn't know how it works with the MDPs with slate, right? We don't know that. But you know how it works with MDPs. So there is, I won't discuss it again. But what I will discuss is that the notion of attention, right? The notion of attention is very important for slate MDPs. Now, if you don't understand attention, you won't understand what is there in the rest of the paper. So now let's give this a break, right? And let's start understanding attention. What is attention in neural networks? Right? So let's give that a break. We'll come back to this once we understand attention. Right? So let's give this a break and start doing attention. So what is attention? Now attention is a topic related to deep learning. Right? It's related to deep learning and it is related to memory, right? Attention, memory. Right? If you relate the terms, you have memory, that's why you can be attentive. Right? So this is a term that has arisen from natural language processing research. Right? So natural language processing research means you have a sentence, big sentence, and you want to translate it. Right? You want to translate it to another language. I think we have discussed what is attention before. Right? So if you want to translate it to another language, then what happens is a particular word might be related to a word in the past. Right? So how can you input such relations? And how can you learn on the go from data that a particular word is related to a word in the past? Right? How can you learn that? So that learning is called attention learning, and this relation is called attention. Right? But how does it come into being? We'll have to look at this. So the beginning, the start, or where I want to start, is a point where I want to model an input. Right? I want to model a signal. Let's say I want to model a signal. So signal is what? Signal is just a time series. You have some data points, right? You have some data points over time, that is signal. So let's go here. Now remember, for your exams, it's just the attention, the notion of attention is there. After that, nothing is there. So whatever we are discussing, we will talk about hidden Markov models, RNN, cell schemes and all that, won't be in exams. But it is needed for you to understand attention, and I can ask maybe very small, short questions on attention. So forget about exam for now. I know it's difficult to forget about exams. But let's forget about exams and let's see whether we can understand, and let's get into a discussion. Maybe I have my understandings wrong. You can tell me that it's wrong, and we will fix it, right? So let's get into a discussion, and let's for the time being forget about exams. Okay? I know it's kind of hypocritical because you can then come to me and say, okay, why don't you forget about grades? But that's how it is. So today is
16.
16. So we need to model. We need to model a signal. How many of you know about regression? You know about regression? We have used it. Regression, we didn't use it. Autocorrelation coefficients. How many of you have? Did you use in assignment 2? Anybody? Autocorrelation coefficients. So you know that, right? So how do you model a signal using correlation? So basically you have over time, right? Let's say IT is a signal over time. This is time and this is IT. This is bad. Why do I have all this? So you have this signal. Then one method of modeling IT is have it as a function of IT minus 1, IT minus 2, and IT minus n. Right? You can have it as a function of this. Or also in case what you can do is you can say that okay, the simplest model is called Sarima or Arima actually. Arima is different. Arima. What is Arima? It's an autoregression model. It's just a linear model. So you express it as a summation of ak I t minus k. Okay. K equals 1 to n, and you can choose some ak's to be 0, some ak's to be whatever. If you choose some ak's to be 0, then that means that memory has no effect. So by choosing ak's, you can do attention. That is basically attention. Right? Which memory you focus on. That is basically attention. But this is linear. Right? This is linear. This is correlation. But how long can you go? How long will you go? That question depends upon how long it takes to learn those parameters. AK, how do I know what is AK? I have no idea. How do I know what is AK? Now this is just a signal, right? And learning AK is a big deal in just a signal. So you need curve fitting techniques and all that you need, right? But this is just a signal. Can you do the same thing for random processes? Can you express the outcome of a random process as a function of previous outcomes? Can you have memories? Right? Can you have a memory in modeling random processes? So what is the one technique that we use, that we have thought of or that we have discussed in modeling random processes? Markov chains. We have discussed Markov chains. Does Markov chain have memory? No. We know that the decision that we take next just depends on the current one. So it doesn't have memory. Can we change Markov chain to have memory? How can we change Markov chain to have memory?
That is linked to the previous actions, the previous states.
So how do what is previous? How do we get previous states? So you have to have some notion of time. How do you get a notion of time? What?
Steps you take.
But just if you do simulation, then you don't remember. If you simulate a Markov chain, you don't remember. Right? So just by simulating over time and connecting link back, you don't remember. So what you have to do is you have to use something called a hidden Markov model. How many of you know about hidden Markov model? HMM. How many of you know about it? So you know. So what is a hidden Markov model? Hidden Markov model is basically multi-layered Markov model. So you have a, okay, now let's go through this with the example. I was going to write it mathematically, but forget about that. Mathematics doesn't serve any purpose. Let's talk about an example. So I just talked about hidden Markov model in another class and I used an example of ice cream and weather, but let's take a different example. So what example should I take? It is very boring to go over the same examples. Let's take an example that. What?
You can take the rain example.
What?
The rain example. Like
Rain?
a person walks in with the and he's wet. What's the chance that it's raining outside whether the sprinkler is on?
No. That won't give us Markov chain, hidden Markov models. Wait.
Rain in umbrella.
Okay, I didn't want to use this example, but let's use it. Sentence, right? No, that might get too complex. Okay, let's use the same example. Okay, fine. Let's say I love ice cream. How many of you are in mobile computing class? It might be very boring now. Let's say I love ice cream. I just discussed this example, but let me make it a little bit more spicy. So let's say I love ice cream and I want to have a model. I want to have a model that predicts how many ice creams will I have today. What will I do with this model? What will I do with this model? Maybe I am diabetic. So maybe I am diabetic and I want to predict, okay, how many ice creams do I take today, and depending upon that I will take that much insulin. Right? Maybe that's what I am doing. But yeah, I want to predict how many ice creams will I have today. But I have no sensors. I have no sensors that detect ice cream, that detect how many ice creams I have today. And you maybe can count, but I don't have any data on that. So how many ice creams I had today is not observed. I didn't observe it. But how many ice creams I had today depends upon a lot of factors. One factor it depends upon is the weather. If it's hot, turns out I have more. And if it's cold, turns out I have even more. No. I have less. Right? It's cold, I have a little bit less. Now, I have a model, I have a sensor, I have a weather data. I have a huge repository of weather data. I know weather data. So from the data, what I can do is I can make a Markov chain to say, okay, when is it going to be cold? When is the next time it's going to be cold? Given that it is hot today, when is the next time it's going to be cold? I can make a model like that. Right? So how will the model look like? The model will look like this: hot, cold, some probability, 0.8, going from hot to cold is 0.2, cold to cold is 0.6, cold to hot 0.4, like this, might be this, right? Now let's say there is another compounding factor. If I have a sore throat or not, right? That also affects whether I will have a lot of ice creams or not. Now, whether I do have a sore throat or not depends upon whether the weather is hot or cold. I am more likely to have sore throat when it is cold. I am less likely to have sore throat when it is hot, right? So if it is hot, then I say that, okay, probability that sore throat given hot is 0.2, probability that no, let's say I can have different levels of sore throat: severe sore throat, mild sore throat, or no sore throat, right? So this is severe sore throat. Mild sore throat, given it's hot, maybe 0.4, and probability that no sore throat given it's hot is 0.1. no, let's make it 0.3 and let's say it's 0.5. So no sore throat is better. Now again, here probability that it is sore throat given cold is maybe 0.6. Probability that mild sore throat given cold is maybe 0.3, and probability that no sore throat given it's cold is 0.1. So what did I do? This is like a belief net. It's a belief net. Given that sore throat is conditionally dependent on hot and cold, both, right? So I can make a belief net of no sore throat, medium sore throat, no sore throat. Right? I can do that. So how I can make a model is like this. So this is a Markov chain. And I have sore throat, medium sore throat, no sore throat, and these are all conditionally dependent. Okay? And I will have probabilities on these. If it is hot and I do have a sore throat, then I can make a another layer here. 1 ice cream, 2 ice creams, 3 ice creams, 4. I don't have 5 ice creams a day, right? So I can have this single ice cream. I can have 2 ice creams, 3 or 4. I can have arrows. Right? Arrows from all of these. Yes. Oh, sorry. Whether I have a sore throat, mild sore throat, no sore throat, I cannot observe. Whether I had 1 ice cream, 2 ice cream, 3 ice cream, 4 ice cream, I cannot observe. What I can observe is this. Whether. This is called a hidden Markov model. Right? This is a hidden Markov model. What is hidden? Sore throat, mild sore throat, no sore throat. It's hidden because I cannot observe it. 1 ice cream, 2 ice cream, 3 ice cream, 4 ice cream is hidden because I cannot observe it. The only thing that I can observe is it's hot or cold. Right? So this is a hidden Markov model. Now how did it model memory? How did it have memory? How did I change Markov model to get memory? The more down you go, the more memory you have. So if you look at this arrow has a memory of, it has 2 information, right? Hot, sore throat. 2 level memory. Same, if you go here, it has 2 level memory. Mild sore throat, cold. So it has 2 memory units. So the more hidden layers you have, more memory you get. Now you consider, if you have n hidden layers, how much information did you get? How many bits of information do you have?
N.
What?
N bits.
No, not n bits. You have n information.
Okay.
N information levels. So how many bits of information? However many bits you need to represent n, right? So that is log n. So you only have log n bits of information. So here there are 2 levels. So log 2, that means it's just 1 bit of information. So 1 bit can be either 1 or 0. So hot or and sore throat, right? So you have log n bits of information for n hidden layers, right? So HMMs can model memory. That's how you can model memory. And HMMs are used to model languages. Language models are typically HMM models. What is a language model? It says that, okay, if you think about English, then it starts with maybe a noun or a pronoun, then it has a verb, it has an article, and then it has an object. So this sequence is a language model. So word order. So now when I try to identify word after word and try to translate it, I might use a hidden Markov model to remember which stage of a sentence I am in. Did I parse a noun? Did I parse an article? Did I parse an object yet? And what I parse next will depend on what I parse all this time, like these three levels. So that's why HMMs are used to keep memory, and they can model language order. So or word order in language models. So for example, to translate from English to some other language, you might use HMMs. Yes?
Here, what would correspond to the words in the language model? What would correspond to the part of speech?
These levels can be part of speech. So words can be, part of speech can be here. So it's noun, and then the probability that you go to a verb is this. And words, what words you use can be the hidden layers. And so given that it's a noun, what is the probability that it is a proper noun? What is the probability that it is a, what is common noun? Right? And then given a proper noun, what is the probability that it is a bus, it is a car, it is a building? Even if it is a common noun, what is the probability that these options? And if it's a pronoun, what is the probability that it's I, you, and so on? Okay. So those will be different levels.
So what do we try to predict in the language model?
What do we try to predict?
Yeah.
So we know that we first do a high level recognition. So let's say I know that this has to start with a noun. Then we say that, okay, noun, is it a proper noun or a common noun or a pronoun? Then the next level say, okay, if it's a proper noun, is it bus, building, car, name, what is it? So that's how we go down. But we have to start from somewhere. So we say that, okay, let's say the sentence starts with a noun. And then we go down. Now after we have parsed a noun, we say that, okay, the next thing that we do is it has to be an article. So let's go article. Is it a, and, the, what? Right? So like that we go. Problem with HMM. The problem with HMM is the bits of information that you can memorize is the relationship with those bits to the number of hidden layers is exponential. So that means that if you have n hidden layers, you only have log n bits. So if you want n bits of information, you have to have 2 to the power n hidden layers. That's a big problem. You cannot have exponentially large number of hidden layers, right? So what do you do? That is one problem. The other problem is a hidden Markov model is just a linear model. It's just a one-to-one correspondence, right? It's just a linear model. Can we have more complex relationships? Can we have nonlinear relationships with the memory? Right? So HMMs don't encode nonlinear relationships. So what is then the next? The next could be we can use RNNs, recurrent neural networks, to model memory. Not only so RNNs can be used to model memory in a much distributed manner. Why? Because each hidden layer can be connected to other hidden layers. So in this case, if you look at the HMM, sore throat is not connected to mild sore throat. Mild sore throat is not connected to no sore throat. These interconnections between hidden layers is not there. But in RNNs, you can have the interconnections. If you have the interconnections, then with lesser number of hidden layers, you can encode more bits of information. That is the advantage of RNNs over HMMs. With less number of hidden layers, you can encode more bits of information. And you can also encode nonlinear relationships with the memory. You can also encode that, nonlinear relationships with the memory. So that is the RNN way to go. So now what is the basic structure of RNN? So in a nutshell, we won't go into the details today because there's not much time. So the basic structure of RNN is like this. So let's say there are some, so it's a neural network, right? So there are some input layers. So input layer has inputs, so say IT minus 1, sorry, t minus 1, IT minus 2, IT minus 3, right? Then you have some hidden layers. You can have as many ones, so deep, right? Go as deep as you can. You put these as inputs. And these are your outputs. So basically, OT becomes a function of IT minus 1 and so on, and this function can be nonlinear. Right? That is in a nutshell what RNA does. But we have to go much deeper than that, because we have to understand what is the problem with RNA. Right? We have to understand what is the problem with RNA, and we have to understand what is LSTM, and then we can go into attention. Right? So there's a long journey ahead. But let's not start the journey today. Let's just stop here. Let's assimilate what we have talked about. And let's again meet Wednesday and we'll then discuss. So the videos, there are 4 videos are left, I think. So your TA is saying that those 4 videos he will upload by tomorrow. Right. There is already a final. I have already uploaded. We can have some discussion. Yeah, I'll discuss next time. In the blackboard is not there? No, so just whatever video is there in the blackboard, just click and
I'm the outside.
More than 4 videos left.
Okay, tayo po.
Yeah.
That's toxic.
No, you take instead of 60% of each user, you take 60% you. Yeah. Each user takes all data, but just takes 60% of the user. And then test on the 40% of the user. All data.
Why not? Wait.
That will help us in encoding nonlinear relationships, and it will also help us in handling lower hidden layers, but still encode more information. No, you don't use RNNs for language. And you can for very complex languages which have for parsing big statements, like 100 words statement. Yeah, that will take a long time. We'll see next class. We'll talk about that.
Later, Tom.
Yeah.
Peace.
Don't worry. Oh, I'm remind me if I don't.
Bye.
Bye.